Curious how to implement state feedback control in real time on real-world systems? Stick around as we break down state feedback implementation step by step with real hardware and all the code you need. And by the end of this video, you'll be able to do it yourself. Welcome to Autis-Tech. Okay, let's get started. DC motors are widely used across modern industries due to their versatility and precise control capabilities. Common applications include anti-lock braking systems, electric power steering systems, radiator cooling fans in automobiles, and various robotic systems. Given their importance in such critical systems, studying the control of DC motors is both valuable and essential. Many of you have appreciated the informative video on state feedback control of linear systems by Brian Douglas on MATLAB Tech Talks, particularly for its clear theoretical explanations. Our video serves as a valuable complement by focusing on real-time hardware implementation, helping to illustrate how the theory can be effectively applied in practice. This video will include the following points: DC motor modeling, state space representation, control design, simulation, experiment, and finally hardware and software description. We start by DC motor modeling, as it is a primordial step for state feedback control design. The DC motor is an electromechanical system composed of two interconnected subsystems, electrical subsystem and mechanical subsystem. Let's start with electrical dynamics modeling. By applying Kirchhoff's voltage law to the armature circuit, we get the electrical ordinary differential equation. Let's move now to the mechanical dynamics modeling. By using Newton's second law for rotational motion, we get the mechanical ordinary differential equation. By combining the electrical and mechanical equations of the DC motor, we form a complete system model. The electrical and mechanical equations of the DC motor form a system of differential equations. This system describes how the current I and angular velocity omega evolve over time in response to the input voltage V. To design the state feedback controller, we need to express our electrical and mechanical equations in a unified framework called the state space representation. For that, we need to define the control variable, the state variables, and the controlled output variable. The armature voltage V is considered as the control signal. The state variables, denoted by x1 and x2, correspond to the armature current I and the angular velocity omega, respectively. These state variables are arranged in a two-dimensional vector x called the state vector. Since our goal is to control the motor's velocity, the output variable is naturally chosen to be the angular velocity omega. Recalling the system of differential equations found earlier, and arranging the equations while considering state variables x1 and x2, besides the control variable u, we get a system of two coupled first-order ordinary differential equations that describe the motor's dynamics. To facilitate analysis and control design, we rewrite the system in matrix form, known as the state space representation. This compact form is essential for modern control techniques, such as state feedback, and is well suited for implementation in simulation and real-time control systems. Next, in the state space representation, we substitute the real physical parameters of the DC motor into the matrices. This results in the following numerical state space model. Now that the state space model of the DC motor has been established, we can proceed to design a state feedback controller. This control strategy uses full knowledge of the system states to compute the input U in a way that drives the system's output Y or omega to follow a desired behavior, such as reaching and maintaining a target velocity R, or also denoted omega D. The state feedback control law can be expressed as a function of both the current state X and reference signal R. Since the state feedback controller is restricted to be linear, it can be written as U equal to minus K times X plus KR times R, where K is a matrix of feedback gain, KR is a reference scaling gain or precompensation gain for steady-state error, R is the reference velocity or the desired value for the output, and X stand for the state vector. This diagram depicts the closed-loop control system employing the state feedback controller. The controller generates the input signal U based on system state X and reference signal R. While the reference scaling gain KR can be computed from state matrices, the feedback gain K need to be determined using pole placement method. Pole placement involves three main steps. 1. Compute the characteristic polynomial of the closed-loop system. 2. Define the desired characteristic polynomial based on the chosen pole locations. 3. Match the coefficients of the two polynomials to solve for the state feedback gain k. We can also place the poles using MATLAB functions like place or acre. Now, with the math formulations established, let's bring this controller to life through simulation and observe its behavior. The simulation demonstrates that while the state feedback controller achieves reference tracking, a persistent steady-state velocity error remains evident. We can notice that the control signal remains bounded within physically admissible limits throughout operation, as required for practical implementation. Now that we've covered the theory, let's move to the experimental phase, where we implement this controller in real time to regulate the velocity of a real motor hardware. Similarly to the simulation, we observe from the experiment that the state feedback controller is able to ensure the reference tracking. But notice the persistent steady-state error between the measured and reference velocity. This is a key limitation of pure state feedback, as it cannot fully compensate for disturbances or model uncertainties. One question that arises is, how can we address this inherent limitation in pure state feedback control? Later in this video, we will show how to eliminate this issue by introducing integral action to eliminate the steady-state error and achieve better tracking. In real-time applications, input scaling through a gain KR is commonly used to eliminate steady-state error. While we have computed this gain based on system matrices derived from motor parameters, this calculation assumes an ideal DC motor model with perfectly identified parameters. In reality, modeling inaccuracies and parameter uncertainties can compromise the accuracy of KR, leading to persistent steady-state errors in the real hardware system. To address this limitation, we will explore the inclusion of an integrator in the state feedback controller to enhance robustness and ensure zero steady-state error, even in the presence of uncertainties. The design of the integral state feedback controller includes 5 steps. Step 1. Defining a new integral state Z that accumulates the tracking error over time. Step 2. Define the augmented state. Step 3. Define the augmented state space system. Step 4. Define the integral state feedback control law, which is defined as U equals minus K x minus the integral gain times the integral state Z. Step 5. Computing the control gain via pole placement. These real-time plots clearly demonstrate the advantages of integral state feedback over standard state feedback. First, the integral version delivers perfect velocity tracking by completely eliminating steady-state error. Notice how it precisely follows the reference signal, where the basic controller fails to reach such performance level. Second, it provides smoother transient response with reduced oscillations and overshoot while maintaining fast convergence. These plots are derived from a separate experiment. As anticipated, the integral state feedback controller demonstrates superior tracking precision over the basic state feedback controller when a reference velocity varies. Let's examine the hardware setup, giving you all the necessary details to recreate this experiment yourself. To implement the state feedback controller in real time, we use the Autis control board, which is currently under development and testing. Alternatively, you can follow this schematic to build your own DIY hardware for controller implementation. This setup has been tested and performs reliably. Want to try this yourself? Find the code in the description below. Here are some of the references used in this video. You can find links to all resources in the description below. Thanks for watching this video. If you have any questions or comments that you'd like us to see, please leave them under this comment so that we get notified and can respond. Thank you for being with Autis-Tech.